This is a very interesting question. There are many different ways to solve this problem. In this video, I would like to show you an approach that starts with an assumption. We'll then use the information given in the problem to analyze the situation and then determine whether our assumption is correct or not. I like this method because it reflects how engineers often approach real world problems. We don't always know what the answer right away, so we begin with a reasonable assumption, carry out the analysis, and then check whether the results support it or not. If they do, we proceed. If not, we revise the assumption and then try again. As we work through this example, I encourage you to focus not only on the calculation itself, but also on the reasoning behind them. Developing this way of thinking will help you approach many engineering problems more effectively. As we discussed in question 10-34, it is convenient to choose the positive directions based on the direction of the initial velocity components. So once defined, this convention will be applied consistently to all vectors in the problem, including velocity, acceleration, and displacement. The projectile is launched with an initial velocity 600 meters per second at an angle of 10 degrees below horizontal. So let's draw it together. I'm going to label it as VI, initial velocity, 600 meter per second, and it's below horizontal. The angle here is 10 degrees. Resolving this into components, we're going to see x direction. We're going to call it VIX, going to the right, and y direction. We're going to call it VIY, and it's going down. Therefore, we're going to define the positive x direction to the right. This is x direction, positive, and positive y direction as downwards. This is y, this is positive. So now let's label two possible landing points as B1 and B2. We put the B1 lies on the horizontal ground and B2 lies on the incline. To begin our analysis, we'll assume that the projectile lands at B1. The reason for choosing B1 instead of B2 is that B1 provides an additional piece of information that B2 does not. The vertical distance of the projectile at the moment it reached the ground is known because we know 628 meters as incline, so we can figure out that. This allows us to apply the standard projectile motion equations more directly. Now let's figure out the geometry of the incline. The incline has a length of 628 meters with a slope of 52 degrees. We can treat this as a right angle triangle. Or the dx, horizontal distance, and the dy is the vertical distance. So dx equals to 628 meters times cos 52 degrees, and that equals to 386.6 meters. The dy equals to 628 times sine 52 degrees, and that equals to 494.9 meters. Now, when landed at B1, the displacement, the y direction displacement of the projectile motion should be the same as this distance y here, and it should be equals to 494.9 meters. And I'm going to use the projectile motion, the standard equations here for the y direction. So we have Sy should be equals to the initial velocity at y direction times time plus half acceleration at y direction times time square. Okay, so let's plug in the numbers. The initial velocity at y direction should be equals to the initial velocity vi, and the y direction, that is a sine 10 degree. And this is a positive number because we define the downwards as a positive y direction, plus half. The acceleration at y direction is gravity. So gravity is going down, and going down is positive. So we have a positive 9.81 again, and then times time square. And this all should be equals to 494.9 meters. Okay, so again, this is a quadratic equation. Let's put the numbers in together. We're having the half 9.81 t squared plus, again, we're just rearranging the orders here, and vi is 600 sine 10 degree times time, and then minus the sy number, so 494.9 meters. Okay, and that's all equals to 0. So it's quadratic equation. You can just simplify it and then solve for the time. And we got two numbers for the time. One is 4 seconds. Okay, and the other one is a negative number, negative 25.2 seconds. The time cannot be negative, so we are not using this one. Discard this one. Okay, so the time for this projectile motion moving from A to B1, that is 4 seconds. Once we got this, we can find out the x direction displacement with it. So x direction displacement for the projectile motion. Remember the x direction, we don't have any air resistance, so there's no acceleration or deceleration there. We're using the constant velocity, which should be equals to the v initial at x direction, and then times time. Okay, so initial velocity at x direction is 600 times cos 10 degree, and then times time. This is a 4 seconds. Oopsie, sorry. Just do this, 4 seconds. And this number, if you do the calculation, that equals to 2,363.5 meters. And to compare with the distance at x direction for the incline, which is larger than this dx number, and the dx number, if you remember, this is 386.6 meters, so it's much larger than the dx for the the x distance for the incline, which means, yes, our assumption is correct. It should be landed on the horizontal ground. If this number here, Sx, is smaller than dx, then the projectile is going to be landed on the incline. So then we need to recalc. So assumption is correct. We don't need the recalc. Then what do we need to do? Well, let's figure out the question itself, asking for calculating the projectile velocity just before landing. Okay, before we landed on B1. Okay, so let's just use point B1 here. So before that, VB at x direction should be equals to, well, remember this is a constant velocity at x direction, so Vix, and this is again 600 times the cos 10 degree. Okay, the calculation comes out with 590.9 meter per second, and it's going to the right. Now the VB at y direction before landed at B1, that's this one has gravity as acceleration. So the equation is VIY, initial velocity, plus acceleration at y direction times time. Okay, again, VIY is going down, so this is a positive one. 600 sine 10 degree is VIY, plus gravity again, 9.81, positive 1, and 4 seconds as the time. So we have 143.4 meter per second, and direction is going down. So now we need to combine these two, right? So we know this VBX is this direction, VBY is this direction, and the actual VB should be a resultant of this two, right? So this is VB equals to, we have VBX 590.9 square plus 143.4 square. This comes out as 608.1 meter per second. Don't forget we need the direction for the vector, so we need this angle here. I call this one theta. So theta angle equals to tan inverse, okay? And we just need the magnitude here. So VBY, which is 143.4, and VBX is 590.9. So this one equals to, equals to 13.6 degree. As a final answer, VB, before it landed at B1, that equals to 608.1 meter per second with an angle. I need to draw this angle for the direction. So here, 13.6 degree. That's the end.